Well, let's talk about this Newton and I think Leibniz is how I usually say it. I'm not. Don't quote me if that's not the official pronunciation there. I can't remember. Leibniz, Leibniz, something like that. So, okay. So what you guys were just talking about, Sir Isaac Newton, says an Englishman, is in from England, not American. Okay, and Gottfried Wilhelm. I don't know. I forget how to pronounce these names here, but Gottfried Wilhelm Leibniz, German, both invented calculus independently of one another in the 17th century. So again, how they did this independently of each other exactly, not 100% sure, but you know. Now, we are specifically talking in relation to derivatives today. To designate derivatives, Newton placed a dot over the y, called y dot. And so, in other words, if we were talking in Newton terms, you would have had a dot over the y to indicate the derivative. However, notice you've started learning a lot about derivatives, and we haven't talked about y dot, have we? You'll notice it says over the years it was changed to prime, which is what we use today when we do y prime, which is the mark that looks kind of like an apostrophe, a single quotation mark, something like that. Okay. Whereas Leibniz, his derivative notation was the dy dx that we use. And you've seen that one as well. He designated the derivative with the dy dx. Now, with the dy dx, we've just used it as a whole quantity, but notice it says to get rid of the dx, he simply multiplied it to the other side to leave dy. And this is the idea of differentials, that usually right now we think dy dx, and we think that means derivative, the derivative of y with respect to x. So the derivative of that y equals equation that has x's in it. But dy dx is a fraction, isn't it? And if it's a fraction, you can multiply by the denominator and separate that fraction into pieces. And that's when you separate those fraction into pieces, dy is called a differential. Those are differentials. So dy is a differential, dx is a differential. Okay? And so we can use that notation. So if you look down in the example there, so definition of a differential. Let y equals f of x be a function that can be differentiated. So when we talk about a function that can be differentiated, that means a function that you can take the derivative of. There are certain functions or certain pieces of functions that you can't take the derivative of. If it says it can be differentiated, that means you can take the derivative. Okay, so I'm not sure how much I've used that word differentiated, but that implies derivatives. The differential of x, denoted as dx, is any non-zero real number. Of course, dx has to be non-zero because it's in the denominator. And the differential of y, denoted by dy, is given by dy equals f prime of x dx. So as we look at the definition, dy equals f prime of x dx. I'm trying to think the way I want to say this, I guess. So side note here, if you think about it gave us y equals f of x, right? So if we're going to talk y equals f of x, then if we take the derivative, well, if we take the derivative of y, then Leibniz is going to use the notation of dy dx, right? If we take the derivative according to Mr. Newton, Sir Isaac Newton, the derivative of fx, how do I usually write that? We usually write that as f prime of x. So now the idea is that dy dx is a fraction that can be separated. If it's dy divided by x, then we can multiply by dx. So if it's dy divided by dx, we can multiply by dx. If you multiply the left, you're multiplying the right by dx. And so the idea, when you clean that up, the dx's cancel, and dy is f prime of x dx. which goes along with definition of a differential. So in other words, what does dy itself equal? The derivative of f prime of x times dx. Now, in terms of, which way do I want to go with this? There's two different ways I could teach this. Maybe I'll take turns and show both. So, okay, so as we look at example 1, example 1 says, okay, and I'm going to try and bring this into play here, but let y equal 3x to the negative 2 plus 2x squared plus 1. Find dy. Well, one option, which is probably the option you're going to be more comfortable with right now, is just to take the derivative as we're used to. So if it says y, and we take that derivative, instead of y, we usually say either y prime or, what do we use to represent derivative? dy over dx. So let's go ahead and go with that idea that, okay, the derivative of the left is dy dx. The derivative of the right. What is the derivative of 3x to the negative second? Negative 6x to the negative third. I feel like Ethan was really having to dig deep there. Derivative of 2x squared? 4x. Derivative of 1? 0, which I don't usually write. Now, the idea is this question asked us to find what? dy. So just using our basic algebra skills, how can we find dy? If it's dy divided by dx, how do we get dy by itself? Multiply by dx. If I multiply one side by dx, we're going to multiply the other side by dx. So a couple of different things here is that, well, first of all, realize on the left the dx's will cancel, and we have dy equals. On the right, and I didn't write it in the previous one, but what can you guess about that dx? It's not just times the last term, it's times the whole side, right? So depending on the situation, this could be a possible answer, okay, where it's dy equals the quantity times dx. The other option is, just like in regular algebra, we can take that dx and we can distribute. So if we distribute it, this looks like dy equals negative 6x to the negative third dx plus 4x dx. Okay, and that's the idea of using differentials. Okay, introducing the concept of them today. There'll be future uses. It's one of those things, you know, introducing the concept today, we'll have future uses down the road. The other way we could have done this, okay, and I felt like what we did was better for you guys because I was using what you knew. But yes, you can go straight from the original problem, straight to the answer. And with that being said, okay, when we say dy dx, the derivative of y with respect to x, we're taking care of the derivative with respect to x by putting the dx here. The other option is, every time you take the derivative of a term, you can then just tag on a dy or dx, whichever one is appropriate for that variable. Meaning, so okay, what is the derivative of y? Well, the derivative of y, just as a variable, is 1, yes? Just like the derivative of x would be 1, the derivative of y is 1, and then since it's y, we're going to tag on the differential dy. Over here, the derivative of 3x to negative 2 is negative 6x to negative 3. What variable did we use? With respect to x, so we tag on a dx. Derivative of 2x squared is 4x. What variable is that? Dx. So in other words, anytime you take the derivative of a y term, put a dy after it. Anytime you take the derivative of an x term, you're putting a dx after it. Because on the flip side, we could also try and solve this for dy dx, where you factor the dx out and you divide the dx over. Okay. Try the next one. And I'm going to take the same route I took last time. But if you want to take the other route and see if you get the same answer, you can. So let y equals sine x plus cosine x. We're being asked to find dy. If we just start traditionally, the derivative of y we say is dy dx, which really it's 1 dy dx. We just don't put that. Derivative of sine x, cosine x. Plus derivative of cosine x, negative sine x. I'm not sure why I wrote a plus there. I wasn't thinking ahead, I guess. How do we find dy? Right. If it's dy divided by dx, we're going to multiply by dx. What I do to one side, we're going to do to the other side. Okay. And final form with what we're doing today, we can distribute. So dx's cancel. We have dy equals cosine x, and we're going to say cosine x dx plus negative, forget that, I'm going to say minus sine x dx. Okay. So the idea of differentials here, okay? The idea of, again, as we go through things this year, there'll be times where we just might want to use differentials, and I'll show you places. But when you take derivative and it's an x term, you tag on dx. Take the derivative of y term, you tag on a dy. And there are reasons we do that. We're not ready for those reasons, but.
So is it cosine of x dx?
Yes.
Cosine of x.
It's cosine x times dx. I see. In other words, yes, this is cosine x times dx. Sine x times dx. No, it's not cosine of x dx. It's not sine of x dx. Good clarification point there. Okay, that's what I thought. That's all I got today, folks.
How about
How about them tests?